Hi friends, welcome back to Wisdom Academy YouTube channel. In the previous video, you have learnt about what is an electric dipole and you learnt what is the electric field due to dipole at various points, at axial point and at equatorial point. And if I remember, the value of electric field due to the axial point was found to be 2 times the equatorial point. E axial was 2 times E equatorial. I also said to you those two derivations are very important for your examination. Today we are going to see what happens if a dipole is kept in a uniform electric field. What happens to it? Does it experience any force? Does it experience any torque? We will talk about that. Fine. So I hope you remember what is torque. From 11th rotational mechanics, you have learned that how torque occurs and what is torque. Let us recall that. Fine. So what I am drawing now? I am drawing a uniform electric field here. Let me name this uniform electric field as E. Okay, and direction of electric field is from left towards right. Now what I will do, I will keep a dipole inside this. Let me keep a dipole. I said you what is dipole? Dipole is an arrangement of two equal and opposite charges separated by a small distance 2d. And I hope you could have understood by now why I took 2d. Since I took 2d, the distance of this from the center was d, and we got the expression as r plus d and r minus d. And finally, you got expression in the most easiest way. If you would have taken the distance as d, then it will be d by 2 and all the equations will become very complex. So, just for the simplicity, we take the distance of separation as 2d. There is no hard and fast rule that you must take 2d only. It is just taken to simplify your things. Fine. So, now I am keeping one dipole, that is one minus q and plus q charge separated by distance 2d. In a uniform electric field, and I am going to see how the force acts on it. So, I said you on that day by the relationship between the electrostatic force and electric field, F is equal to Q into E. So, this charge plus Q, since the electric field is in this direction, plus Q will experience a force Q E in the side. This minus Q, since it is negative Q, it will experience a force in this direction. I'll write it as minus QE. Since I'm using minus, just know the direction, magnitude is QE only. So, two charges which are equal and opposite, they will cancel out each other. Am I right? So, these two forces QE and minus QE will cancel out each other, and we can know that net translatory force will be 0 on this dipole, since this plus QE and minus QE will cancel out each other. Then will the dipole experience no other force? Let us see that. So what happens if I draw a line here and keep it like this? This is theta. So I can find what is this side. So sine theta equal to, what will be sine theta? Let us see. So sine theta will be equal to BC by AB. What is AB? AB is 2D. So from here I am getting BC is equal to 2D sine theta. Remember this, right? So now we have seen that whenever there is a force acting at any object which are acting at two ends and they are equal and opposite, it tends to move the object. I will say rotate the object. So this is the object and it is acted upon by a force on this direction and this direction, it starts rotating. If they are equal and opposite, it forms a term called as couple. You studied in 11th standard. So what is couple? Couple is the arrangement of equal and opposite forces which tend to rotate the body. It rotates the body in the same axis, since these two forces are equal. If these forces would have been unequal, it will rotate and it will start moving ahead. That is called as rolling. So rolling happens if the force acting at the ends will be unequal and opposite, right? So here it is equal, so it will be acted upon by a rotatory force called as torque. And what is torque? From our knowledge of 10th I am writing torque is equal to force into perpendicular distance, right? So what is the force here? Force is QE, magnitude of force is QE. I am writing magnitude of torque. And what is this perpendicular distance? That is BC. So I got the value of torque as QE. What is BC? 2D sine theta. Now you can see from here that q into 2d makes a dipole moment. So I got torque is equal to magnitude of torque is equal to magnitude of dipole moment into E into sine theta. Now I know that A cross B is equal to AB sine theta. From there I can write torque, vector form of torque is equal to P cross E. This is the expression of torque. So torque is equal to P cross E, that is, it is the cross product of dipole moment and electric field. Please keep this in your mind. And one more thing you notice here, see from the formula of torque, if theta is equal to 0, what will be torque? Torque will also be 0. And when theta is equal to 90 degree, what will be torque? Torque will be equal to PE. So torque will attain a maximum value when the dipole is placed perpendicular to the direction of electric field, because what is theta? Theta is the angle made by the dipole with the electric field. So if you want your dipole to have the maximum torque, then you must place the torque perpendicular to the direction of electric field. If it is kept parallel to the direction of electric field, definitely it will not be acted upon by any torque, because theta is 0, torque is 0. One more thing you must keep in your mind, that this is the torque for a dipole only if it is kept in uniform electric field. So if it is kept in non-uniform electric field, formula will not be same, because it will be acted upon by a translatory force also as well as rotatory force, so it will be having a different nature. Fine. So this formula, whatever we are using, it is valid only for uniform electric field. Let us see one question now. Calculate the field due to an electric dipole of length 10 centimeter and consisting of charges of plus or minus 100 microcoulomb at a point 20 centimeter from each charge. So this kind of questions, you should read the question very carefully before attempting it. So there is a dipole, and dipole consists of plus or minus 100 microcoulomb. So this is minus 100 microcoulomb, this is plus 100 microcoulomb. Length of dipole is 10 centimeter. So this length is 10 centimeter. I get it as 0.1 meter in SI units. Fine. Then they have told you have to find the electric field at a point 20 centimeter from each charge. So from each charge it is 20 centimeter. It is possible only if it is somewhere here, and this they have given us 20 centimeter, and this they have given us 20 centimeter. Mind that they have not given the value of R to you. This is R, right? R is not given to you. But do we need R for this question? Let us see. I don't think we need R, because the formula of E equatorial is, see here can we use that formula. The formula of E equatorial was K into P by R cube, the magnitude of E equatorial. Can we use this formula here? No, we cannot use. Why we cannot use? Because this formula is valid only if R is much higher than D. In this case, you see D is 5 centimeter, R is definitely less than that, but less than 20, but comparable. So R and D, since they are comparable and they are not much different, we should not use this formula. It will lead to a wrong answer. So what we should do? We should use that formula. And what was the formula? It was K into P by R square plus A square the whole power 3 by 2. Remember this formula? This formula was E equatorial formula, magnitude of equatorial, and direction was anti-parallel to this dipole length. Right. Now, see, they have given the value of root over R square plus D square as 20, isn't it? If this is R and this is D, this is root over R square plus D square, isn't it? So this means R square plus D square power 1 by 2 is given as 0.2 meter. So R square plus D square power 3 by 2 will be cube of this 0.2 cube. We can use directly here. So the value of E equatorial will be equal to, K value is 9 10 power 9, P is Q into 2D. Q is 100 into 10 to the power minus 6, and 2D is 0.1 divided by this value is 0.2 the whole cube. So when you solve this, you will get the answer of electric field at this equatorial point, Newton per Coulomb. This is the way you should solve this question. It is a very simple question, but mind the words that will give you an idea where the case is a case of equatorial field or axial field. Let us see one more question. This question was asked in NEET. A point P lies on the perpendicular bisector of an electric dipole of dipole moment P. If the distance of P from the dipole is R and they have given the condition that R is much greater than the length of the dipole, what is the electric field at P? Or they have asked the electric field at P is proportional to what? So it is a question of equatorial field. They have taken two charges and distance between them is whatever 2d and minus q and plus q, and they have told that the point P lies on the perpendicular bisector. So somewhere on the equatorial line it lies, this point P. So they are asking you to find its proportionality with that. So we know for this condition, and since they have given R is much greater than 2d, we can write very conveniently that E equatorial is equal to K into P by R cube. Got the answer? See, they are asking the proportionality of K. K is a constant. If R becomes a constant, then E equatorial is proportional to P, right? And if P and K are the constant, then E equatorial is proportional to 1 by R cube. So that can also be written as E equatorial is proportional to R power minus 3. So R power minus 3 and P, D is the answer. The next topic is electric lines of forces. So before I enter into the properties of the electric lines of forces, what are these electric lines of forces? The concept of lines of forces was introduced by Michael Faraday. Why he did so? To visualize how is the nature of electric field and magnetic field. So what he visualized is when any positive charge is kept in any field, electric field, how it tends to move, that will give the electric lines of force. And thus he defined the electric lines of forces as the path in which a positive charge will tend to move when it is left free in a electric field. That curve or that line will give the lines of force. And he also told that if you draw a tangent to these lines of force, at that point it will give the electric field of that particular charge or of that particular thing. So to find a direction of electric field, we have to draw a tangent on these lines of forces, right? Let us now see what are the properties of electric lines of forces. The first property, they are continuous and smooth curves. So you can relate all these things to your 10th standard of magnetic lines of forces. I think you can recall from there. Similar points were there in your lines of forces of magnetic field also. Same things, similar things will come here. So first thing is they are continuous smooth curves. Second thing is they start at positive charge and end in the negative charge. So from all the positive charge, they will look to be starting like this, and in any negative charge, it will be ending. So if there is no pair of charge and there is only single charge, then it is assumed that it starts from the positive and goes toward till the infinity, and if it is a negative charge, from infinite it comes and it gets converged to the negative charge. It goes like that. Third point is same thing what I told now. Tangent to this line gives the direction of electric field at that point, and this point also says that no two lines of force will cross each other, because if suppose there are two lines of forces like this and we assume that they have crossed each other, then at this point, due to this line, if you draw a tangent, this is the electric field direction, and the same point, this is electric field direction. Can at one point be two directions of electric field? No. That's the reason two electric lines of forces will never intersect each other. The relative closeness of these lines gives the measure of strength of electric field. So if these lines are closely spaced, we will say it is a strong electric field. If they are far spaced, they are weak electric field. And it is same thing as written here. Closed, if they are closed, very close, it is strong field. If they are far apart from each other, it is a weak field. If it is parallel and equally spaced, like how I drew in the previous cases, this is a uniform electric field. This is a representation of uniform electric field. And the last point is, since electric field inside a charge connector is 0, they don't pass through it. How electric field inside charge connector is 0, you will learn in the upcoming class. And this is also the concept of electrostatic shielding, which we will be learning in the coming class. So with this, I want to wind up today's class. What we learned today? Today we learned about the torque on an electric dipole when it is kept in a uniform electric field, and we found that whenever a particular dipole it is kept in a uniform electric field, it experiences a torque. There is no translatory force, but there is a torque, and value of the torque, the magnitude of the torque was Pe sin theta. In vector form, tau vector is equal to P vector cross E vector. Then we saw a few numericals based upon that, how it is asked. We also solved one question which came in NEET, which is very simple, and then we learned what is electric lines of forces and what are the properties of electric lines of forces. With this, I would like to wind up today's session, and in the next session, we will be learning further about Gauss theorem, right? So please keep on practicing. I have covered almost 70% of the first unit. I expect you to take the books in your hand and start solving all the questions. And if you have any doubt, you can go back to my previous videos and get clarified in that. Thank you very much.